This is our second extra help video for Test 8, and this video is going to focus on scientific notation and scale factors. So this particular example is number 2 in your study guide. We need to compare 5.93 times 10 to the negative fifth and 4.31 times 10 to the negative fifth. Now, it would be really helpful in order for us to compare these two things to write them in standard notation. So we're going to turn each of these numbers into standard notation. Now, if I have 5.93 times 10 to the negative fifth, I'm going to use 5.93. And this number up here tells me how many units and in what direction to move the decimal point. So I need to move the decimal point negative 5 units, which means 5 units to the left. So I'm going to move it 1, 2, 0 right there, 3, 4, 5. So I've got zeros in all these empty spaces. So 5.93 times 10 to the negative fifth is 0.1, 2, 3, 4 zeros, 0, 0, 0, 0, 5, 9, 3. Now I'm going to do the same thing for 4.31 times 10 to the negative fifth. So I'm going to use 4.31, but this tells me how many units and in what direction to move the decimal point. So I need to move the decimal point negative 5 units. 1, 2, 3, 4, 5. There's my decimal point. And then I fill in those extra spaces with zeros. So this is the same thing as 0 point, and then 4 zeros, 4, 3, 1. Now we need to compare these two and say which one's larger, which one's smaller. They're certainly not equal. So if we look at our decimal places, we start with the first one. They're the same, so we move to the next one. Again, same. Next one, still the same. Next one, still the same. Still the same, and here is where we find the difference. Now notice that the 5 in this same decimal place is greater than the 4. So that means that our first scientific notation number is bigger than our second one. So the symbol we would use here would be 5.93 times 10 to the negative fifth is greater than, because this digit is larger, than 4.31 times 10 to the negative fifth. And that would be our solution for that one. Now let's look at number 13 in your study guide. Now here we are multiplying two scientific notation numbers. And scientific notation works just like all other multiplication problems, meaning the commutative property still applies and the laws of exponents still apply. So here I've got 5.6 times 10 to the fifth times 4.1 times 10 to the sixth. So those parentheses aren't really doing anything. I could say that would be the same as 5.6 times 10 to the fifth times 4.1 times 10 to the sixth. And then I can use my commutative property to make this a little more clear about how we're going to go about it. So 5.6 times 4.1 times 10 to the fifth times 10 to the sixth. Now notice right here we have like bases. So it's kind of like if we had x to the fifth and x to the sixth. If we were going to do that, we would just add their exponents. So that's what we're going to do with that 10 to the fifth and 10 to the sixth. We still have 10, and we're going to add their exponents, 5 plus 6, to get 11. Then over here, we're going to multiply 5.6 times 4.1. So when we do that on our handy-dandy calculator, we get 22.96. So now we have 22.96 times 10 to the 11th. Now I know that that looks like in scientific notation, but in order for something to truly be in scientific notation, this number over here has to be between 1 and 10. Now 22.96 is not between 9 and 10, so we need to figure out where can we put the decimal point so that that number will be between 9 and 10. And the answer is right here after the 2. So 2.296 is between 1 and 10. And then I need to know how many units and in what direction do I move this decimal place to get it back where I started. And since I move it 1 to the right, I have to add 1 to my exponent, right 1. And 11 plus 1 is 12. So that's why the solution there is 2.296 times 10 to the 12th power. Now let's look at just writing a number in scientific notation, and this is number 16 on your study guide. We just want to write this number in scientific notation. So the way we do that is we look at our number and say, where can we put a decimal point so that that number will be between 1 and 10? So I know that if I put my decimal point right here after the 1, that I'll have 1.234, and that will give me a number between 1 and 10. Now I know I'm going to have to multiply by 10 because we do that in all scientific notation. And to determine the power, I decide how many units and in what direction do I have to move this decimal point to get it back where it started. Now originally that decimal point was at the end there. So to get this one back, I have to move it 1, 2, 3, 4, 5, 6 units to the right. So since it's right 6, I'm going to use a positive 6 as my exponent. And now I have 1,234,000 written in scientific notation. Now let's check out 17. 17 was the word problem, so this was probably a trickier one. And the question said, the speed of light is 3 times 10 to the 8th meters per second. If Mars is 2.25 times 10 to the 11th meters from the sun, how many seconds does it take light to reach Mars from the sun? And we want to write our answer in scientific notation. Now, the distance formula, which has come up lots of times in class, is really handy for this one, and here's why. We have the speed of light. Now, speed and rate are the same thing. And then we have distance from the sun. So we have rate and we have distance, and we're looking for how long will it take this light to reach Mars. So we're looking for an amount of time. We're going to use the distance formula to solve this. Remember, distance equals rate times time. Now, we don't know the rate and the time. We just know the rate and need to find the time. So since we're looking for time, I'm going to go ahead and solve this equation for time by dividing both sides by r. So time equals distance divided by rate. So if I want to find out how long it takes light to reach Mars, I have to take the distance from Mars to the sun and divide it by the speed at which that light is moving. Now the distance from Mars to the sun, as we just read, is 2.25 times 10 to the 11th meters. And we want to divide that by the rate or the speed at which that light is moving, which up here is 3 times 10 to the 8th meters per second. All right, now when we do this, again, laws of exponents still apply. So we have 10 to the 11th divided by 10 to the 8th. And since those have the same base, we can subtract their exponents. 10 to the 11th divided by 10 to the 8th would be 10 to the 11 minus 8. And 11 minus 8 is 3. So we're going to use 10 to the 3rd. And then we need to divide 2.25 divided by 3. So when we do that, 2.25 divided by 3, we get 0.75. So now we have 0.75 times 10 to the 3rd seconds, because our meters will cancel here. Now this looks like it's in scientific notation, but again, this first number needs to be between 1 and 10. So where can I put the decimal point in 0.75 so that it will be between 1 and 10? So if I put my decimal point right here, I have 7.5, which is between 1 and 10. So that's the number I'm going to want to use. Now, since in order to get this decimal point back to where I started, I have to move it 1 to the left, I also have to subtract 1 from the exponent. So the new exponent on my 10 is going to be 3 minus 1, or 2. So it will take 7.5 times 10 to the second seconds for light to reach Mars from the sun. Now we're going to move on to the scale factor problems. First scale factor problem we're going to look at is number 7. Now number 7 says a model airplane is constructed using a scale factor of 1 centimeter to 75 centimeters. If the actual airplane has a wingspan of 12 meters, how many centimeters long is the wingspan of the model? So we've got our scale factor and we've got our actual length. We want to know the length of the model. Now please note that our scale factor is in centimeters. Our answer needs to be in centimeters, but the actual length we're given is in meters. So first we're going to have to convert 12 meters to centimeters to make our lives easier here. Now we have 12 meters, and in 1 meter there are 100 centimeters. So my meters cancel, and I've got 12 times 100, which is 1,200 centimeters. All right. Now, every scale factor problem that we've done so far basically boils down to a proportion. So in this one, when the model is 1 centimeter, the real airplane is 75 centimeters. Now, what we have is a real length, or a denominator, of 1,200 centimeters. And we need to find the model length in centimeters. So we've just set up a proportion using our scale factor. 1 centimeter in the model is 75 centimeters in real life. X centimeters in the model is 1,200 centimeters in real life. And to solve a proportion, we just cross multiply. So when we do that, we've got 75x equals 1 times 1,200. Now guys, it's really important that you remember when you cross multiply, you don't create a new fraction, you create an equation like this one. So we've got 75x equals 1,200, and when we divide both sides by 75, we get x equals 16. So if this is our scale factor and the actual airplane has a length of 1,200 centimeters, then our model length will be 16 centimeters. And here's the last example for this video. It is number 15. It's the same sort of deal here. Now we have a scale drawing of a kitchen tabletop. And the dimensions of the drawing are 5 inches by 2 inches. The scale factor of the drawing is 1 inch in the drawing equals 18 inches in the real table, and we want to know the dimensions of the actual table. Now, we have our scale factor, and that's what we always use as our first fraction for our proportion. So 1 inch in the drawing is 18 inches in real life. We know that for the first dimension, the length, we have 5 inches in the drawing, and we want to know how long will it be in real life. So I'm going to call that x inches. Now we've set up a proportion, and we can just cross multiply and solve. So we have 1x equals 18 times 5, which is 90. And of course we can divide by 1, we don't really need to, but x equals 90 inches. So our length would be 90 inches. Now we've done that for the length, and we have to do the same thing for the width. So we have the same scale factor, 1 inch over 18 inches, and the width is 2.5 inches in the drawing, and we need to know how big is it in real life. So again, cross multiply. We've got 1x equals 18 times 2.5, which is 45. So the width of the table is 45 inches. And so that means that the real dimensions of our table are 90 inches by 45 inches.